Hello. In today's lesson in Chem 1, we are going to switch gears from thermodynamics, where we're looking at the energy before and after a reaction takes place, and switching into something called reaction rates, which is technically called kinetics. Kinetics being the speed with which a reaction goes. Just, like kinetic energy is energy in motion. This is the reaction itself in motion. And we're going to describe reaction rates by looking at something called collision theory, which collision theory is really an extension of kinetic molecular theory, which we saw back with gases, and we hinted at a little bit when we were talking about solids and liquids as well. So, what is a reaction rate? It's the rate at which reactants disappear. Of course, reactants are being used up in the reaction, or products appear. Right, so reactants are disappearing because they're being used up. Products are appearing because they're being produced. And the way we're going to measure reaction rates is by measuring a change in the concentration. Concentration with a change in time. So change in the concentration, where I'm introducing a new notation here. These square brackets, look down below here, the square brackets. If I put some chemical A into the square brackets, this notation means the concentration of A, so whatever A is, in moles per liter, or molar. So this is a shorthand way of not having to write out concentration of A, and we can make it nice and easy to write out. So what we're looking at here is a change in the concentration of the products with a change in time. Any rate is going to have a change in time. So rate of motion is the change in distance with a change in time. Change in mass, change in other things. You can always measure a rate with change in time. Or the change in the reactants with a change in time. And for the reactants, we're going to have this negative sign here. And it's negative because the concentration of the reactants is decreasing. So we actually wanted to make the rate into a positive number. So the negative makes the rate positive. The concentrations of the products are going to be increasing as you'd expect them to as the reaction proceeds. Now, this is a little complicated here. The only reason I'm showing this graph is to give you an idea of how we might look at the reaction rates. We're never actually going to be calculating reaction rates, except for in our lab. You will be calculating the rate of the reaction based on the starting and final concentrations, but that's all you're going to have to worry about. What I just want to show you here is that for this reaction, and this reaction we have is 2N2O5, which is a gas, is decomposing into 4NO2, also a gas, and 1 oxygen, which is also a gas. All right, so we've got this reaction going on, and we're starting off high on the concentration of the N2O5. So let's see, what color do I want to use? Let's use the light blue here. So here's our N2O5, and we're starting off with only the concentration of the N2O5. Notice on the y-axis, we've got concentration in molar. So we could put here, this is the concentration of the N2O5. Oh, there it is over here. I didn't notice that there. The concentration of the N2O5 decreasing. And as the concentration of N2O5 decreases, we can pick a spot. Let's for convenience sake, pick the spot that they've got highlighted here, and we can take the average slope over that time as being the rate of the reaction between 300 and 400 seconds. So between 300 and 400 seconds, the decrease in the concentration is negative 0.0019 molar. The time is 100 seconds. And so we'd get a rate for the reaction in N2O5 of negative 1.9 times 10 to the minus fifth molar per second. Just a little math there. Now, if we look at the NO2, and that's our green line, so the NO2 is coming up. Again, you'd expect the NO2 to be increasing because it is a product. Oh, what happened there? And between 300 and 400 seconds, the increase in the NO2 is about twice that, or for the decrease in the N2O5. And that's just because of stoichiometry. So the stoichiometry, so the ratio is going to be 4 to 2 times the rate of the N2O5, or twice as much. And finally, for the red line, that's the oxygen. Down here, O2. The O2 increases at a rate that's about half that of the N2O5. And again, that's because of stoichiometry. That's about 1/2 the rate of the N2O5. Again, we're not going to be doing anything with that. I just want you to notice that and realize that those stoichiometric coefficients do have application here. The other thing I want you to notice is that as the reaction proceeds, so between 100, let me go back to green, between 300 and 400 seconds, we have one rate, and what's that line there? We have one rate, and then as we proceed further along, between 600 and 700 seconds, the rate has decreased. So this is always going to be true, that the rate always decreases. And we'll find out more about this tomorrow, but that's going to be because the rate depends on the concentration of the reactants. And because the reactants are being used up, that rate, that concentration also decreases. Now, like I said, we'll talk more about that in our next lesson. For now, let's talk about, well, why do reactions happen? That's one of the things we haven't talked about yet. What is it that we need for a reaction to take place? So it might make sense to you that in order for a reaction to happen, the reacting molecules have to collide. They have to come together in some way. I like to use an analogy of cars on the road, and cars driving down the road, they pass by each other all the time with no interaction, with no change. When they do interact, we call that a collision, and the collision is what causes the change to happen. Well, that's a change we don't want. When it comes to molecules and reactions, generally we do want something to happen. So the collision is important, but it's not enough. We also need to have enough energy. So the reactants have to be moving fast enough. Again, cars that bump each other very lightly going at 1 mile an hour aren't going to cause a lot of damage. And if they hit bumper to bumper, they're going to cause even less damage. So we also need the correct orientation. And in this diagram here, I've illustrated a couple of examples of collisions that are or are not what we call effective. So down below on the left-hand side, let's suppose we have this theoretical collision between A molecules and B molecules. And what we want to have happen is we want to have two AB molecules coming together, and they're going to form an A2 molecule, and 2 B atoms are going to come apart. And what we're showing here is that in this first reaction, notice that there's no change. So 2 ABs went in, 2 ABs came out. Now, assuming that in order for a reaction to happen, we have to have the 2 A atoms, those 2 small A atoms, have to somehow come together so that they can attach. And that's one part of it. That's the correct orientation. So we have the correct orientation. But the other part of it is this. In order to get those A molecules off the B molecules, off the B atoms, we need energy. We need energy to break the A-B bond. And if the energy is too low, so in this case, the energy is too low, no reaction occurs. NR, meaning no reaction. And we get energy that's too low when the temperature is too low. So this is going to be a lot about temperature in here. We call that an ineffective collision. In this second one, we don't really care what the energy and the temperature. And by the way, this is energy. So this is energy that's at the temperature. Let's start marking that as kinetic energy. Kinetic energy is too low. And so in the middle, it doesn't really matter because you can see that those 2 A atoms are far apart. And there's no way that they're going to come together because it's not only enough to start breaking the AB bond. We'll talk about this in a moment. You have to break the AB bond. You also have to start forming the 2A bonds, and the AA bond. We'll talk a little bit about that in a moment. So this is the wrong orientation. And in this wrong orientation, then we have no way for those bonds to do what they're supposed to do. This is actually the most likely collision. It's going to be rare to have those 2 A atoms exactly where they're supposed to be. So most collisions do not result in a reaction happening. Most collisions no reaction happens. All right, finally, in this last diagram, we have our 2 A atoms coming together side by side. And because we've got our products, there's our product, our A2 and our 2B atoms. Now we have what's called an effective collision. What does an effective collision entail? It has the correct orientation and sufficient kinetic energy to break those A-B bonds. All right, so now we've got ourselves set up to figure out how to apply this collision theory. So if you turn the page, you will see a new kind of energy diagram. Well, actually, it's the old energy diagram. We're going to get to that in a moment, and we're going to modify it a little bit. The activation energy is the energy that I've been talking about. This is the energy needed to start breaking the reactant bonds. Now, delta H only addresses the potential energy, and on the diagram down below, we have the potential energy going from the reactants to the products. So the delta H always goes from the reactants down to the products. But there is something else that we need to do to indicate this activation energy, this energy needed to start the reaction. And the activation energy, EA, and I'm sorry, I thought I got rid of those proofing symbols. I guess I didn't. It doesn't like that EA. There we go. The activation energy. We're going to call that the minimum energy needed. Let me redo that. I can't write. Minimum energy needed. And we're going to modify this in just a moment for reacting particles to react. So we need to have that amount of energy to react. And this energy comes from the kinetic energy of the particles. It's something extra we need to have to get the reaction started, such as a spark or a flame. This is why wood burning that has a very high positive change in entropy, lots of gas is formed. It's very large exothermic reaction. So it's a very spontaneous reaction, but it doesn't occur at any appreciable rate until you apply a spark or a flame. And that's because it has a high activation energy. So activation energy is going to be put onto this curve as a hump. It's a block, if you will. It is something that it's a hurdle to get over. And we're not going to go straight down from the reactants to the products like we have before. We're going to modify this now, and we have to go from our start, we have to go uphill. We have to go up to get to the top. And here's what I've got. We're going to finish this up in a moment. Here's what I've got showing here. I've got OH minus and CH3Br are coming together. And in order to start reacting, we need two things. We need to start forming a bond between the water and between the oxygen and the carbon, and we need to start breaking the bond between the carbon and the bromine. That's what takes energy, and that's the energy. We can draw that as an arrow here, pointing up to the top, and label that EA. You can also draw it, if you want to, over here. It's the same height. All right, so we have the activation energy to get up to the top of that hill. So if this was a ball that you wanted to roll downhill, it'd be a little energy that you had to put in to get that ball to roll up to the top of the hill first, before you could then roll it downhill. At the top of the hill, we have this thing called an activated complex. Or a transition state. This is a very important part of the reaction. You can kind of think of it as halfway between the reactants and the products. It's kind of a combination of reactants and products. And what we've got going on is the reactant bonds. In this case, only one reactant bond. Reactant bonds are breaking. And as I hope you've gathered by now, breaking bonds is always an endothermic process. So we have to put energy in to get that to happen. That's the activation energy. And then the product bonds begin to form. And that's the exothermic part of it. And when those product bonds finally form, then we come down off the hill. That wasn't a very good diagram. Oh well. We come down off the hill. Let me redo that. That looks kind of bad. I wasn't sure where I was ending up. There we go. That's a little bit better. We come down off the hill and we form our products. And in the products now, we've formed that bond between the carbon and the oxygen, and we've made CH3OH, which is methyl alcohol, and we have a bromide ion come off all by itself. So this activated complex is a high energy state. This activated complex can't be collected. But we can see it with chemical techniques. Now let's go back up to our definition of activation energy, and let's modify it just a little bit. It does say it's the minimum energy needed for reacting particles to react. It's the energy needed to attain the activated complex. So it's how much energy it takes to get to that top. And even once you get to the top, you're not assured that the reaction is going to work. It's a 50-50 shot. 50% of the time, you'll go forward and complete your reaction, and 50% of the time, you'll go backwards. All right, so I think I've got a whole bunch of things down below that we got to fill in here. So the activated complex is a combination of the reactant and reactants and products. It's temporary, it's unstable, as I said, you can not collect, but can be observed. And this is how people have started to understand how chemical reactions occurred. And here's the next thing about this. The reaction is reversible. That means at any point along here, you can go backwards, even starting from your products. So in the reverse direction, we can start with our products. And let's see, what color can I use for that? Let's use light blue. So I can go the reverse direction. I can go from my reactants back to my products. But to do that, actually, that's not a good place to draw that. To do that, that's actually not too bad. I'm going to need to put some more energy in. So for the reverse reaction, the activation energy in the reverse has a little extra hump there because it now has the delta H in the reverse plus the activation energy in the forward direction. So different activation energy, the reverse activation energy equals the delta H in the reverse direction plus the EA, the activation energy, in the forward direction. It's got to be larger in this case because the forward reaction is exothermic. Let's use the same color. Forward reaction is exothermic. Exo in the forward direction. That means when we turn it around, going the other direction, it has to be endothermic. And endothermic reactions always have this higher activation energy. And a reaction like this can proceed to the right, can form products because the rate of the reaction depends on the activation energy. A higher EA means more kinetic energy needed, and that means a slower reaction at the same temperature. So since our products and reactants are at the same temperature, the reverse reaction here is harder. So the reverse reaction is harder, and essentially we make products. If we tried to go in the reverse direction, we could redo those reactants. However, we're not going to be as efficient in doing it. All right, so transition theory, transition states, and activation energy, all part of collision theory. And there will be some questions on the worksheet that have to do with things that I think are going to be important for you to know. Have a good rest of your day, and I'll see you next time in class.